Hi everyone and welcome back to NTE. In this video what we're doing is we're giving ourselves a chance to practice some electrochemistry. Right. So with this one we are focusing on questions from November 2016, right? And we're looking at question 8 and question number 9. Right. Okay, so question number 8, right? 8.1 says a nickel rod, right, is placed in a beaker containing silver nitrate solution, right, which has the chemical formula AgNO3. Okay. And a reaction takes place, right? So we're obviously going to have to figure out which reaction takes place over here, right? Just notice that this is just a reaction that's going to occur in a beaker, right? So this reaction is actually not doing any work whatsoever. Okay, but if you actually disconnected these two things right into two separate beakers, then you could do some work with this reaction in terms of it being a galvanic cell or a battery, right? So before we actually even jump to the questions, let's move on to table 4a and just identify which reaction is going on over here. We're going to have to identify nickel on our table and also silver. Okay. Right, so as previously stated, the standard reduction potential table is table 4a at the back of your exam papers. Right, so like I said, we're looking for nickel and we're looking for silver. So those two things are metals, so they're going to be below the standard hydrogen half reaction. Okay, so we can start looking from here. Right, so there is nickel. Okay, and we need to compare it with silver. So if we look for silver quickly, okay, so silver is not below hydrogen, so we have to look above. Oh, there it is. Okay, so there's silver. All right, so I'm not going to be able to get both of them on the screen at the same time, but basically nickel is below silver, right? So just remember, we're going to now use our direction arrows, right, to just give us an indication of who is stronger and who is weaker. Okay. Yes, basically the way I use this is I take it and I imagine it to be on the middle right of the table like this. Okay, so when I look at my direction arrows, it's telling me that silver plus ions, okay, those ones are stronger oxidizing agents. Okay, and if we scroll down, you'll see that the direction arrow is telling me that my strong reducing agent is going to be nickel. Right, so this is a strong reducing agent. Okay, right. So now that we have that jotted down, okay, remember that the strong people are always the ones that win. Okay, so which means that that nickel rod, right, because we have solid nickel that has been placed into that silver nitrate solution, right, that nickel rod is actually going to undergo oxidation, okay, because it is a reducing agent. Okay, and then some of the Ag plus, right, that is in solution, okay, that's going to undergo reduction and become silver, okay, just pure silver. Okay, right, and once equilibrium is reached, that process will stop basically. Okay, so for question 8.1.1, again we have the instruction write down the name or, right, don't write both. Okay, write down the name or the formula of the electrolyte, right? So the electrolyte is basically the substance or the liquid that can conduct electricity, right? In our case, that is this substance right over here, AgNO3, okay, or silver nitrate solution. Okay. Next, write down the oxidation half reaction that takes place. We already noted that the oxidation half reaction is going to be that of nickel, right? So when we write it down, it's just going to be straight from the table, nickel going into nickel 2 plus, right, and it releases 2 electrons. Okay, notice that when you're writing down the half reactions, you only use a single arrow, right? On the table, you've got those equilibrium arrows, but when you are actually stating a specific reaction, you use a single arrow. Okay. 8.1.3 says write down the balanced equation for the net overall redox reaction that takes place. Okay, so in order for us to do that, we need the other reaction as well. So I'm just going to write it over here. Okay, we identified that the reduction reaction that occurs over here, right, is the Ag plus gaining an electron to become solid silver, and the oxidation half reaction is the nickel solid, right, going into nickel 2 plus and releasing 2 electrons. Okay, so what they want us to do here is to write the net. Okay, alright, so net is having all of the other spectator ions, which is the NO3, or the nitrate ion in this case. So basically what I'm going to have over here, right, when I add these two, I'm going to have the ionic, right, reaction. Okay, so first of all, we need to balance this, right? So you can see that we just need to times the first reaction by 2, okay, to give us 2, 2, and 2. Okay, so now the electrons cancel each other out, right, because one of the electrons is reactants and in the other reaction the electrons are products. Okay, so if we get this ionic reaction down, it's going to be 2Ag plus nickel solid, giving you 2Ag solid plus nickel 2 plus ions, right? But they wanted the net. Okay, so which means that we just need to add in the spectator ions, so which balance out these positive charges on our cations, right? So the net ionic reaction, okay, over here, right, we're going to have 2, right, and we just need 1 NO3. Okay, we still have the nickel, right? Okay, and that's going to go to 2Ag. Okay, and now for over here, right, we're going to need 2 of these nitrate ions to balance out the 2 plus charge on the nickel. Okay, question 8.2, right, it now says a galvanic cell is now set up using the nickel half cell and a silver half cell. Okay, so basically what they're doing now is, because they realize that there's a reaction happening, right, when you combine Ag plus ions with a solid nickel rod, right, now they actually using this to do some work, right, which is to produce electricity. Okay, so this is a battery. Okay, right, so question 8.2.1, it says which electrode, right, the nickel or the solid silver electrode must be connected to the negative terminal of the voltmeter, right, give a reason for your answer, right, so the negative terminal of the voltmeter is on this side, that's the positive terminal. Okay, well, it has to be the nickel, right, because the nickel is the one that has to undergo oxidation. Okay, so it does actually say give a reason for your answer. You can give the reason that we stated when we went to table 4a, right? Nickel is a stronger reducing agent. Question 8.2.2, right, it says write down the cell notation for the galvanic cell above, right. Cell notation is basically going from the anode to the cathode. It's not really so much of a big deal, right? We basically telling a story, right? We have that nickel solid, right, is going to go into solution and become, draw a line, nickel 2+ ions, right, due to oxidation. And then we have our salt bridge, okay, and then on the cathode side, right, there goes the electrons, okay, here they come, right, on the cathode side, the Ag plus ions that are in solution will get attracted to the cathode, right, and be reduced to solid silver. Okay. If you want, right, you can put in the conditions, right? So the fact that these ones that are in solution, right, have to be in a 1 molar concentration, okay, and you can also put in the states. Okay, so I'll just show you what that will look like. Okay, but you can see how that first cell notation that we wrote down is much quicker, right? But if you want to add this extra information, you can, right? So question 8.2.3, right, it says calculate the initial reading on the voltmeter if the cell functions under standard conditions, right? So they're basically wanting us to calculate E naught cell in this case, right? So we need to go back to our table and jot down what is the standard reduction potentials, right, for the oxidation half reaction, sorry, and the reduction half reaction. Okay. Okay, so from the table we have to jot down this value, right, for the reduction half reaction of silver, that is plus 0.80. Okay, and we also need to jot down the standard reduction potential for the reduction of nickel 2+ ions, right, and that is minus 0.27. Okay, right, so here we go. Right, so this is now going to go into the formula. E naught cell, right, is equals to E naught cathode minus E naught anode, right, and all that these two subscripts mean is just the reaction that's happening at the cathode and the reaction that's happening at the anode, right? So now we're going to make this specific to our situation. Okay, I've jotted down the information from the table above. Okay, we know that at our cathode we've got the reduction of silver plus ions, right? So that's E naught, or the standard reduction potential of silver plus ions to silver. Okay, then we need to minus from that the reaction that's happening at the anode, right, and that is the oxidation of nickel, right? But over here what we are considering is the standard reduction potential, right, of nickel 2+ ions going to solid nickel, right? So one thing you need to note over here is that that whole process that we did before of balancing the electrons, that is just to write the net reaction. Okay, it doesn't affect anything when it comes to these standard reduction potentials, right? You don't multiply these values by 2 in any way. Okay, so then from there we just substitute. Okay, so E naught cell is going to be equals to, this one is plus 0.80 volts, and we need to minus from that, this one is minus 0.27. Let me not put in these volts, they're a little bit confusing. Let's just put in the values. Okay, right, so then this works out to be 1.07 volts. Okay, so the standard cell potential is 1.07 volts. Okay, are we happy that this standard cell potential is positive. Yes, we are, because we are working with a galvanic cell. Okay, just note that this, wanted to write here, this is from table 4a. Okay. Now, question 8.2.4 says, how will the voltmeter reading, right, in question 8.2.3, right, so the one that we just calculated, be affected if the concentration of silver ions is increased, right? Choose from increases, decreases, or remains the same. Okay, so what they are saying is, what will happen if we increase the concentration of silver plus ions in this half cell over here? Okay, so basically what will happen is that the voltmeter reading will increase, right? Now let's go to our half reactions to explain why. Okay, so now just focus on this reduction half reaction, okay, for silver. Okay, so what did they say? They said that we are increasing the amount of silver plus ions in solution. Okay, so notice the equilibrium that the system is trying to keep over here, right? So if you increase the amount of silver plus ions in solution, okay, then the system, right, we now applying the theory that we know from chemical equilibrium, right? The system is going to favor the forward reaction, okay? So which means that more solid silver is going to be coated on that cathode, right? So in order for more solid silver to be coated on the cathode, right, it means that more electrons have to be delivered, okay, to the cathode, right? Now that you know that we have more electrons that are delivered, okay, right, so first of all, realize the fact, or remind yourself, that 1 volt, okay, is equals to 1 amp times ohm, okay, and this comes from the equation V is equals to IR, right? Okay, so now what have we done? We want to know what's going to happen to the volts, right? We are now delivering, or we are requiring more electrons to be delivered, so we are increasing the amount of amps, okay, so then the voltmeter reading is also going to increase, since volts and currents are directly proportional, right? Okay, so going back to this question, luckily for us, we don't really need to give a reason. They just wanted us to choose from increases, decreases, or remains the same. We just figured it out that this is going to increase. Right, question number 9 from November 2016, right? It now says that in the electrochemical cell below, right, carbon electrodes are used during the electrolysis of a concentrated sodium chloride solution. Okay, so what do we call concentrated sodium chloride solution again? If they ever ask you, it's called brine. Okay. All right. Anyway, all right. So this is sort of like an upside down experiment over here. Right. So analyzing this situation further, right, we have to note over here that this sodium chloride is in solution, right, AQ, which means that we have, because it's concentrated, we don't have that much water, but water is present in this, okay? And then we've got some Na plus and Cl minus ions in the solution. Okay, this is table salt basically. Right. Okay, so they further give us over here that the balanced equation for the net overall cell reaction that is occurring over here, there you go, there's the water, right, liquid water, plus Cl minus in solution, okay, giving you, there we go. So that's one of the gases. We're just going to have to identify where is it, right? Is it gas X or gas Y? Right, we've got some chlorine gas, and we also have some hydrogen gas, right? And then you have hydroxide ions in solution. Okay, so notice something else about this net cell reaction. Okay, the Na plus ions show up nowhere over here, right? So what does that tell us? It tells us that the Na plus ions are spectator ions. Okay, question 9.1. Is the reaction exothermic or endothermic? Okay, so these are very easy marks, and please don't mess them up, right? It's just basically applying theory, okay? Like you saw in the previous video, okay, galvanic cells are always exothermic reactions, okay. Electrolysis, right, remember that electrolysis is the electrochemical process that is used to drive non-spontaneous reactions, okay. So you obviously need to put in energy for those reactions to occur, right? So if you are putting in energy into a reaction, it means that that reaction is endothermic. Okay. Question 9.2. Is the electrode P the anode or the cathode in this experiment? Well, we're going to see that by looking at our battery, right? So electrode P is connected to the positive terminal of this battery, making it the anode. So our answer here is that P is the anode. Okay. Says give a reason for your answer. The reason is because this is an electrolytic cell. Okay, question 9.3. Right. Again, we have this write down situation. 9.3.1, the name or the formula of gas X. 9.3.2, the name or the formula of gas Y. 9.3.3, the reduction half reaction. Okay, so the reduction half reaction is going to be the reaction that occurs here, right, at electrode Q, because Q is the cathode, right? So we just need to figure out what is actually happening here in order for us to answer all of those questions, right? And for that, we need to go to table 4A, okay? When we get to table 4A, what are we looking for? We're looking at this overall cell reaction. We're looking for water, okay, that is somehow in equilibrium with hydroxide ions, right? And we are also looking for somehow in equilibrium with the hydroxide ions and the hydrogen gas, and we're also looking for chlorine gas. Okay, right, so here's our table. Let's go searching. Nope, this one is not going to work. All right, so there's the chlorine. Nice. Scrolling down, this water has oxygen, so that's not going to work. Scroll a little bit down. That's peroxide, so that's not what we're looking for. There's a hydroxide ion, but there's oxygen there, so that's not going to work. Okay, so when you scroll all the way down, you will find the half reaction that has water, hydrogen gas, and hydroxide and ions. Okay, so that is way below where you find the Cl minus. Okay, so you can already start imagining. Okay, these are direction arrows. Okay, strong oxidizing agent to the left and up, strong reducing agent to the right and down. Okay, but now here's the catch, right? We only look at strong oxidizing agents and strong reducing agents when we are looking at a galvanic cell, right? Because a galvanic cell, the strong people win, right? Because there we're looking at a spontaneous reaction. With electrolysis, right, we're looking at a non-spontaneous reaction. Okay, so what happens here is a reaction between a weak oxidizing agent and a weak reducing agent. Okay, so we can still use these direction arrows, right? Basically, if the direction arrow is telling you that chlorine gas is a strong oxidizing agent, it means that chloride ions, okay, those are going to be weak reducing agents. Okay, now scrolling down, all the way down, okay, over here the direction arrows were pointing down to this side, telling you that these components here, right, the hydrogen gas, if you have it in combination with the hydroxide anions, those will be a strong reducing agent. But then we don't want strong things for electrolysis, so on the other side the water, okay, is a weak oxidizing agent. Okay, so now that you've identified that, basically all that you need to focus on now is the fact that water is an oxidizing agent, right? So oxidizing agents undergo reduction, right? So then this reaction is going to go in the forward direction like that, right? And then the other one, okay, the Cl minus ions are reducing agents. Reducing agents undergo oxidation, so then this reaction is going to go in that direction. Okay, so I'm going to jot that down on the side over here on our page, just so that it's easier for us to reference. Okay, so now we're ready to answer these questions, right? So we are now going to see that, okay, they want us to write down the name or the formula of gas X, right? So let's go back. Right, so gas X is being formed here at the anode. What happens at the anode? Oxidation, right? What did we identify as our oxidation half reaction? Well, it's the oxidation of Cl minus ions. So then gas X is going to be chlorine gas, right? So Cl2, that's the answer for there. And now gas Y, right? Going back, there's gas Y being produced here at the cathode. What happens at the cathode? Reduction. Okay, so we identified the reduction half reaction to be the reduction of water, right? So then it means that gas Y is going to be the hydrogen gas. Okay, so there it is. Okay, and then lastly, write down the reduction half reaction. It's basically that. Okay, so straight from the table. If I just quickly look at the balancing here, okay, I missed a 2 in front of this hydroxide. Okay, because we have 2 oxygens there. Okay, so it's just a mistake from here. Okay, so moving on to the last question, right? Question 9.4, it says, is the solution in the cell acidic or alkaline, right? Which basically means basic. After completion of the reaction, give a reason for your answer. Okay, so for this, we just need to basically go back to the diagram. Okay, so what we said is that over here at gas X, right, what's coming out is chlorine gas, right? And at gas Y, right, what's coming out is hydrogen gas, right? So you are basically losing from the solution, right? The Cl minus ions. You might not be able to lose all of them, but you lose some of them, okay? And then you're also losing, okay, if we go back to the reduction half reaction, what's happening here at Q, electrode Q, sorry, right, from that water, right, you are losing some hydrogen and you are basically producing hydroxide ions in solution. Okay, and we all know that these two, right, basically the components of sodium hydroxide. Okay, and sodium hydroxide is a base. Okay, so to answer this question, is the solution acidic or basic? Right, it's going to be basic. Basic because, right, because we are seeing an increase in hydroxide ions in solution. Okay, these will be balanced by the Na plus ions. Okay, to form a solution of sodium hydroxide. Right, so then that's it for today's video, matriculants. That's all the electrochemistry right from November 2016. I hope you guys learned something, and I will see you guys next time.